In the previous ring video, the V means I was unable to solve this one, so let us solve this one first today. So we have the ring Zn where addition is addition modulo n and multiplication is multiplication modulo n. In this, if one takes a subgroup under addition, then that is also automatically a subring. That's what we have to show. So let H be a subgroup of Zn under addition, any subgroup. Since Zn or Zn is a cyclic group, under addition H is also cyclic, because we know from the results on cyclic groups that any subgroup of a cyclic group is cyclic. So H is also a cyclic group. That means it has a single generator. Let H be generated by the element G. Where G is some element in our original group. Now the elements in H are what? If you follow the multiplicative notation, you know that in this cyclic group the elements look like this: integral powers of G, where n is, we cannot take this n because it's already chosen for modulus. Say a general element in H looks like this, where I is some integer, and we know what this symbol means. If I is 0, then by definition this is the identity. If I is a positive integer, then this means a product of I copies of G, and if I is a negative integer, then this means a product of minus I copies of G inverse. But keep in mind that since the operation we have in this group and the subgroup is addition modulo n, so this Gi usually is written as Ig. And also recalling that the binary operation is addition modulo n, this actually is G plus G plus G. I copies of G. If I is a positive integer, and where this plus is not ordinary plus but addition modulo n, the binary operation. In that sense, we have this subgroup. So the general, and we don't usually write it like this, we write it as Ig, and that's what we are going to write here. Now we need to prove that this H is a subring. So because it's already a subgroup, we just have to show that if we take any two elements from H, their product, which of course that product is using the multiplication modulo n, that binary operation, that product must again be in H. So let Ig and J G belong to H, where I and J are integers. Then if we take their product, in the ring Zn, then that product can also be written like this. Now this is the result which in general is true in any ring, and we need this result here, which I am not going to prove. The result is just simply this. Say you have a ring R with unity. Oh, do we need unity? No, there is no need for any unity. You have any general ring R in which you take two elements A and B, and you can of course define IA, JB like this. Where I and J are integers. Then this is true. Note carefully that this is not any one of the two rules of exponents. The rules of exponents are in a group itself. Okay, I mean, if you have a group G in which you have an element G and say you have integers I and J, then one rule says this and the other one says this. This is not any one of these two. That is because in this equation we not only have the addition of these rings Zn, we also have the multiplication, because you see this IA and JB, these are two ring elements here, or in fact here in this general situation, and we are taking their product using the ring multiplication, and here on this side between A and B also we have the product in the ring, and this IJAB has the same meaning, a similar meaning as IA. IJ, keep in mind, is again an integer. I and J are also integers, but A and B are general ring elements. So we have used this thing here, and now because of the speciality of this situation, that this G is also an ordinary integer, we can in fact interpret this GG in two different manners. They will both give us the same thing, but we can interpret GG either as the product of the two integers G, I mean G square modulo n, or you can interpret this thing as this thing like this, where the second G is considered to be coming from Zn and the first G is an integer. So if for example G is a positive integer, then actually G will be a positive integer, because it is coming from Z. It can be 0 also. Say G is a positive integer, then this means adding G copies of G. So if you interpret this thing like this, then you also get this. In this step we have in fact used this part among these two rules of exponents, we have used this one. because if we don't write this element like this additively, if we decide to write it multiplicatively, it looks like this. And in its place we are right. This may look very strange, okay, but keep in mind that this is not actual power. This is because we are writing the thing using multiplicative notation, that's why. Yes. Okay, so you see that ultimately again this is an integral power of g, so it will belong to h. And that is why, because h is also closed, besides being a subgroup under addition, it is also closed under multiplication, so it's a subring of Cn. Next exercise 41, because we solved till 40, only this one was left out. Let M2Z be the ring of all two by two matrices over the integers, and let R be the set of matrices that look like this. Prove or disprove that R is a subring. Note that the 2 by 2 zero matrix belongs to R, because 0 minus 0 is also 0, and this 0 is integer 0. So that means R is a non-empty subset of M2Z. Subring, subgroup, these things first of all must be non-empty subsets, and then only you go for verifying the other conditions. If you are not sure whether the subset is non-empty, then your efforts may go in vain. maybe the definition of the subset is quite complicated, not as simple as this, and you don't put some effort in verifying that the subset is non-empty. If it turns out to be empty, then it's not a subsystem. Okay, so now we can first show that it's a subgroup under addition and then closed under multiplication, so it will be a subring. It will be a subring in this case. So let since everything ultimately depends on the entries, we start by taking the entries. Then the sum of these two matrices A plus C, A minus B plus C minus D, so you can see that this can be written also like this: A plus C minus of B plus D. So this clearly belongs to R. Then the additive inverse of one of these matrices is minus A minus B. Now this is going to be B minus A, so which we can also write as minus A minus minus B. This belongs to R. And what happens if we multiply these two matrices? AC plus this times this, which I mean we can do the multiplication directly. AC minus AD minus BC plus BD. First row, second column, AC minus AD plus AD minus BD. Second row, first column, AC minus BC plus BC minus BD. Then second row, second column, AC minus AD minus BC plus BD. Minus B minus D is plus BD and plus BD. Okay, Now this becomes what? 2AC minus AD minus BC plus BD. AD and minus AD cancel out. We are left with AC minus BD. Here also minus BC and plus BC, they will cancel each other and we will be left with AC minus BD. And here AC minus AD minus BC plus BD is 2BD. The entries are integers, of course, but what about this minus this? Let's just see. 2AC minus AD minus BC plus BD minus this, that means minus AC plus AD plus BC minus 2BD. 2AC minus AC give us AC plus BC minus BC, they cancel out, plus AD minus AD, minus 2BD plus BD is minus BD. So yes, this minus this is actually this and also is actually this. So this matrix has the form and hence it belongs to R. So that is why R is a subring of the ring of 2 by 2 matrices over the ring of integers. Hence so this turns out to be a subring. Next, let again another such exercise. Let R be the set of 2 by 2 matrices of this form where A and B are integers. Prove or disprove. Again, just like the previous solution, the 2 by 2 zero matrix belongs to R, so R is a non-empty subset. This R, however, is different from that R. Then so here the matrices are arguably simpler than those ones. So this clearly belongs to R. This also clearly belongs to R. And what about multiplication? AC plus AD. Again AC plus AD. BC plus BD and BC plus BD. So this has the required form to be in R, so it is in R. Hence, here also R is a subring of this. Next, let R be the direct sum of 3 copies of the ring of integers. So that means the elements in R are ordered triples of integers, and in this ring addition and multiplication are defined component wise. And S be the subset of R consisting of those triples A, B, C in R, of course, or that should be mentioned, such that the sum of the first 2 coordinates equals the third coordinate. For this S, prove or disprove that S is a subring of R. This system will not be a subring. Let us see why. It is not closed under multiplication. To show that, we just need to consider 2 elements in S whose product is not in S, for which you can consider things like this. This ordered triple and this one both belong to S. Why? Because the sum of the first two coordinates equals the third one in both of them, but their product, and product is component wise, is 1 times 2 2, minus 1 times 3 is minus 3, and 0 times 5 is 0. This does not belong to S because 2 minus 3 is not 0. Hence S is not a subring of R, although I think it says subgroup of R under addition. Exercise 44. Suppose there is a positive even integer n such that the nth power of a is equal to a for all elements a in some ring. Some ring has this property that the nth power of every element equals the element itself. Show that minus a equals a for every a in that ring. In that ring, minus a equals minus a whole to the power n because of this hypothesis. It's true for every a, so in particular for minus a also it is true whatever a is, and because n is a positive integer, so this is a product of n copies of minus a. Now use the fact that n is not just a positive integer but a positive even integer. So using elementary properties, elementary things that are true in a ring, this will be equal to this, and Oh, by the way, I should, okay. Actually, we can, we not only we can, we have to. We have to write it as a to the power n. I cannot bring minus 1 into the equation because 1 may not be there in the ring may not have a unity. The thing here that is happening is this. You know that in a ring, this is, or more generally, this is equal to AB. So here we have two factors. Here we have an even number of factors. So the negative sign does not, it vanishes. And this again is equal to A. So that's why minus A is equal to A. (45) Let R be a ring with unity. Show that the set S consisting of elements which look like this is a subring of R. So this is that thing that we were discussing when solving exercise 37, that this n dot 1 is 1 plus 1 plus 1, n copies of 1 are being added if n is a positive integer. 0.1 is by definition 1, and if n is negative, then it means adding minus n copies of minus 1, where this n is an ordinary integer but this 1 is the unit element in the ring. This one is not necessarily an integer. In this case, we can clearly see that the set S is non-empty, so we don't bother to mention that. For any two integers n and m, we have n dot 1 plus m dot 1 is equal to n plus m dot 1 minus of n dot 1 is equal to minus n dot 1, and the product of these two elements equal this. which is nm dot 1. Do you see what this equation is? This equation is actually one of the laws of exponents, rules of exponents. If we don't decide to write this binary operation, this rule of exponent is in the group R under addition. If we don't decide to write this binary operation, that is, if we use the multiplicative notation, then this same equation will look like this. So that is why it is one of the rules of exponents. So this is true. This is also coming from the other rule of exponents. And if we decide to write it like that using multiplicative notation, the left hand side will look like this, and the right hand side will look like this. So these two are coming from the rules of exponents in the additive group of the ring. And this is that thing that I said back when we were discussing the solution to exercise 37. Now this fact we used there also, here also we are using. So I urge you to prove this fact. To prove this in a general ring, you have to apply induction on any one of these two integers, n and m, keeping the other fixed. It's not very difficult, it's quite easy actually. So we see that the sum, also the product of any two elements from S is again in S, also the additive inverse of any element in S is also in S. Hence S is a subring of R. Here the solution ends, and here the video also ends. In the next ring part from Gallian, we will see more exercise solutions, and tomorrow we have analysis. So see you tomorrow. Have fun with mathematics until then. This is me, Lucifer, from a mathematical room. Have a nice night.